Hello students. So today we are going to study an important topic of electrochemistry, that is Latimer diagram. So let us first see what exactly is this Latimer diagram. Okay. So this Latimer diagram is actually a potential diagram. Okay, it's a potential diagram which gives you the relative stabilities, the relative stabilities of different different oxidation states of an element. Of an element. Okay. So let us see this, what exactly it is. So here, if you look at the definition, it is a potential diagram. Okay. So diagram in the sense here, it is a simple arrow diagram. Okay, which gives the relative stabilities of different oxidation states. You know, an element can have variable oxidation states, right? So especially when you consider D block elements or some of the P block elements also, they will have different oxidation states. So it gives you what is the relative stability of them. Okay, so here not only that, one is to get the relative stabilities, and also from this diagram, we can calculate we can calculate the potential of a particular half cell reaction. A particular half cell reaction. Okay. So we can calculate a potential, so that we are going to see by taking some examples. And then here, along with the relative stabilities of different oxidation states, we can also predict whether the disproportionation reaction takes place or not. Takes place or not. This also we can predict from the diagram. So three things we can do actually. One is relative stability, and then whether the disproportionation takes place or not. And we can calculate the potential of a particular half cell reaction. Okay, three things we can do from the diagram. So it is very useful in electrochemistry. So now let us see first how to calculate this potential of a half cell reaction. Okay, we'll see this point first. Then we'll go to relative stabilities and disproportionation. Okay, so see, in order to calculate the potential of a particular half cell reaction, so what I mean here is, I'll show you one example here. Look at this. So here you can see a simple diagram. This itself is Latimer diagram. Okay, what is written? We have Cu2 plus, we have Cu plus and Cu. You can see an arrow mark from Cu2 plus to Cu plus and Cu plus to Cu, right? And you can see the potentials written over the arrow mark. First one 0.15 volt and second one 0.5 volt. Okay, and here this is a question wherein they have asked the potential when Cu2 plus gets converted to C. Okay, for this half cell, they are asking the potential. It is given as X volts. Okay, so where we have written the species like this actually, Cu2 plus 2 Cu plus and 2 Cu, and here you can see the potentials written. That itself is the Latimer diagram. Okay, so now let us see how to calculate this potential. Okay. So see, when you calculate the potential, actually when you look at the reaction, you assume that first potential is given 0.15 and second is 0.5. So simply we can add to get the potential of this total reaction, right? But it is not so, because this potential is an intensive property. It is an intensive property. Right. So you know what is the meaning of intensive and extensive properties. Intensive property means it does not depend on the amount of substance or quantity of matter. Okay. So you cannot add these intensive properties directly. Right. See, for example, if you take temperature. Okay, temperature is also an intensive property. So if I have a cup of water, okay, so that is at say 50 degrees Celsius, and I have another cup of water that is also at 50 degrees Celsius. Okay, so if I mix these two, the temperature doesn't become 100 degrees Celsius, right? That means it is not additive. Okay, that's the meaning of intensive property. I hope you understood this. Similarly, the potential is intensive. You cannot add them directly. Okay, so what else we can do here? Instead of adding the potentials, we know one relationship between Gibbs free energy change and the electrode potential. That is, we have delta G is equal to minus NF E, right? Or you can write at standard conditions delta G naught equal to minus NF E naught. Right, this is the relationship we have. Here delta G naught is the standard Gibbs free energy change. Then N is the number of electrons involved in that particular reaction. And F is Faraday's constant. You know, it is 96,500 coulombs. And E naught is the electrode potential. Okay, so now this delta G naught is an energy value, and the energy values are extensive. Energy values are extensive. That means they are additive. We can add them. Okay. So what we do here is we can add the energy values of first step and the second step in order to get the energy of the third step. That means delta G naught of third step you will get. And from that, by knowing the value of N and F, you can calculate the E naught. This is the basic idea. Okay. So now actually what happens when this type of question is given, what you will do is you will directly take say delta G naught for first reaction, then delta G naught of second reaction, right? You will take like this. Say if I write delta G naught for first one, that is from Cu2 plus to Cu plus. So there minus, see Cu2 plus to Cu plus means how many electrons? Here one electron is involved. So 1 into F is anyway a constant, you write it as such, and into you write this 0.15. Right, 0.15 volt. Then similarly you will do for second step. So in second step you have plus 1 to 0. That means again one electron is involved. Then into F. Then into you have 0.5. Okay. So then later on what you do is you need this thing, third one, for the overall reaction. So now overall reaction means you have two electrons involved, right? From Cu2 plus to Cu. So minus I have 2 then into F, okay, then into I have E naught of third one. We don't know this value, we need to find out. Now what happens is while substituting, see you have negative sign and all that. So actually what delta G3 naught is equal to delta G1 naught plus delta G2 naught. Right. So you have to do it this way. Then what happens? This will be equal to this plus this. So when you add this and when you calculate, here some mistakes may happen. That is while cancelling the terms, while adding or while considering the negative sign, you will miss something and you will end up in some other answer. There is a possibility. Okay, so instead of going with this approach, we can simplify it before and we can have a simple formula actually at the end in order to calculate the potential. So I'll tell you that way here, which is a shortcut method. Quickly by looking at the reaction, you can calculate the potential. Okay, so what I'm doing actually is, see, I have delta G1 naught actually. I'll write it as minus N1 F E1 naught. Okay. Then delta G naught I'm writing minus N2 F E2 naught. Then delta G3 naught, that is for the overall reaction, I'm writing N3 minus N3 F E3 naught. Okay, now let us do this. Delta G3 naught is equal to delta G1 naught plus delta G2 naught. Okay, so just write this formula itself I'm writing. So E3 naught, this is equal to minus N1 F E1 naught. Then here also you get minus N2 F E2 naught. Right. So now you can see that minus sign and then you have this F, right? That is Faraday's constant, that is common. Okay. So you can cancel that. Minus sign is also common. Faraday's constant is also common. When you cancel, what remains is N3 E3 naught is equal to N1 E1 naught plus N2 E2 naught. Right, because minus sign cancels. Then what I get? E3 naught is equal to N1 E1 naught plus N2 E2 naught divided by N3. So this is the final direct formula to calculate E3 naught. Okay, so sometimes what they do, E3 naught they'll give, they might ask E1 naught or E2 naught. Whatever is asked, you can calculate from the same formula. That means we are taking the number of electrons and the electrode potential. That's it. We are not concerned about anything else. So let us take this question now. So in this question, you see here, as I told you, one electron is involved. Here also one electron is involved. And in the overall reaction, we have two electrons involved. Right. That means if I take E3 naught is equal to N1 is 1 here into E1 naught, the first potential 0.15, then plus again 1 electron into I have 0.5. So multiply by 0.5, then divided by, you have N3, that is total number of electrons, which is 2. So just multiply it and add. Here anyway it is 1. So 0.5 plus 0.15, that is 0.65, and divided by 2, that is 0.325 volt you will get. Okay, so this is the final answer we got. So we got the value of this X. Okay, so we have found E3 naught here. So that's all. How we find the E3 naught is, we use this formula directly and find out. Okay, now you see one more thing here. If in this formula, if all these number of electrons are equal, say N1, N2 and N3 are equal, then what happens here, N1 and N2, if they are equal, you can take that N1 common. Again, N3 is also same, so you can cancel that and you can write E3 naught is equal to E1 naught plus E2 naught. That means when the number of electrons are equal, you can add them directly. Okay, for the overall reaction, I'm adding these two directly. That you can do. But here the number of electrons were not equal. Two cases it was 1 and the third case it was 2. Right? Okay, now let us take one more example so that it will become more clear. Yes, so here is the question now. This is given in a different way. That means the diagram is not given. The question is given. So we have to write it in the form of diagram. So what is the standard potential of this electrode? Okay, so you can see from the question, it is getting converted from TL3 plus to TL plus, right? And what is given, what else is given in the question? We have TL3 plus to TL plus. That means the intermediate oxidation state is this plus one. Okay, so I'll write TL3 plus that gets converted to TL plus, then to TL. Okay, so we have TL3 plus to TL plus. So that electrode potential is given here. So I'll write 1.26 volt. And then TL plus to TL, that is also given. Now it is minus 0.336. Okay. Now what we need is TL3 plus to TL. Okay. So this is asked. Okay. Now we already know what we have to do. So 3 plus 2 plus 1. That is, here we have 2 electrons involved. And if you consider this one, TL plus to TL, here only 1 electron is involved. And in the overall reaction, plus 3 to 0. So it is 3 electrons are in. Okay, let us directly take the formula now. So we need to calculate E3 naught. For that, E1, that is this value, into number of electrons plus this value into 1 here and whole divided by total number of electrons, that is 3. Okay, so if you simplify this, you will get 2.184 divided by 3. So the final answer will be 0.728 volt. Okay, so we got the final potential for this particular electrode. So you can use this method in order to calculate the electrode potential in a Latimer diagram. So that's all for today. Thank you so much.